about how to and that was the only thing I had in my phone.
West? Forrest Brown? West Hines?
I don't know.
Okay, let's begin. Let us begin. It's my privilege to welcome you to the University of Tennessee Nuclear Engineering Department Colloquium Program. Today's speaker is Dr. Forrest Brown, who is the team leader for Monte Carlo development and the Diagnostic Applications Group of the Los Alamos National Lab. Forrest received his BS and MS degree in physics from RPI, and then he went into the nuclear Navy for 4 years, and he was an instructor in the Naval Nuclear Power School. After his stint with the Navy, he went back to graduate school at the University of Michigan and got a PhD in nuclear engineering. After that, he went to work at the Knowles Atomic Power Laboratory in upstate New York, which is a naval nuclear propulsion R&D lab, and he was there for 15 years. After his stint with Campbell, he spent 2 years at the Argonne National Laboratory, and more recently, he's now been at Los Alamos, with Los Alamos National Lab for the past 5 years. Somebody asked me before the presentation today, how did we justify getting Forrest here? How were we able to get him here? And I think the reason we were able to get him here is because he and I have been friends and colleagues for over 20 years. And I've wanted him to come for quite some time, and so we finally selected a date. The title of his presentation today is MCNP5 and Monte Carlo development at Los Alamos. And so, Forrest, welcome.
Thanks, Lee. Do I need? You just pushed the wrong button. Takes a while to adjust to it. It's okay. Holding your hand is keeping your hand. Let me have it. I can do it. There we go. Okay. Good afternoon. For about the next 30 or 40 minutes, I'd like to tell you some of what we've been up to at Los Alamos with our Monte Carlo development team. Partly, I'll talk to you in the next few minutes about who we are developing the Monte Carlo at Los Alamos, but I'm going to sort of start at the top and just say a few words about Los Alamos in general, and then about the particular program that we're involved with that funds all of this work. That's the ASCII program of the Department of Energy, and then talk about some of the details of what's new with MCNP, version 5 of MCNP, and what the motivation was for doing that, as well as how things are turning out. And then at the end, I'd like to talk to you about, just give you some highlights of some of the basic research in Monte Carlo that we're doing. This is all basic research that supports MCNP in some fashion. Tell you about things that we're doing now that may take us, in some cases, a few months, in some cases, a few years to actually get into the code. So again, talk briefly about Los Alamos itself and the ASCII program, then MCNP5, and then some general things about Monte Carlo eigenvalue calculations. Los Alamos. The lab has been around for more than 50 years, and it's located here in New Mexico, northern New Mexico, about 7,400 up
It's actually the whole region is a desert region, but there's a lot of interesting things in northern New Mexico. I've shown on here just assorted pictures of things that go on in the area, and for Lee's benefit, I put the golf course on there. And at the moment, our golf course has been open for about a month. Also, our ski hill, which is only a few miles away from the golf course, is also open. So there's lots of things going on. I enjoy it very much. This is a panorama view of the lab, and the town itself is right over here. The lab is spread out over something like 43 square miles in the mountains, 7,400 feet up, and you notice mesas all over the place, and the town and the lab are on the mesas. The canyons in between are sort of off limits to anything. They're too hard to get at. So the lab's a big place. Lots of things going on. The basic purpose for Los Alamos, and most of the work we do, at least 2/3 of the work we do, has to do with what's called stockpile stewardship. We do experiments and calculations to make sure that the stockpile weapons is safe, reliable, and will do what it's supposed to do. A good part of the lab focuses on threat reduction, reducing threats to the U.S., mainly dealing with weapons of mass destruction. Another part of the lab is devoted to cleaning up things that were done in the past. And then about 1/3 of the lab looks at general things which are difficult technical challenges for the country in the area of energy, environment, security, and so on. So there's lots of different things going on at the lab. About 14,000 people work at Los Alamos. The part of things that I'm involved with has to do with simulations. Simulations of experiments and other things on some of the largest computers in the world. I've shown on here the 5 computers that we principally use today, and they're not all at Los Alamos. The red machine, we call it, is at Sandia National Lab. The white machine, a big IBM system, 12 teraops. That's at Livermore National Lab. Same with the Blue Pacific machine, 3 teraflop machine. Blue Mountain, which was the computer that we got about 4 years ago, they started to install it. 3 teraflop system with 6,000 processors on it. And that's essentially our workhorse today, where we do most of our big calculations. And the machine at the lower right is partially installed. 20 teraflops is on the floor working, and we get to play with that. Another 10 teraflops is being installed right now, so the total will be about 30 when we're done. These machines are used for some very large simulations that support our role in the stockpile stewardship area. Very large 3D simulations. A couple of years ago, the focus for all of our work was really being able to do full-blown calculations in 3 dimensions, time-dependent calculations in 3 dimensions. Over the last couple of years, the emphasis has shifted more and more to getting more realism in the calculations, better and better physics. Okay, we've taken care of the 3D problem. We've taken care of running in parallel on thousands of processors. So what we're interested in right now is better physics, better answers, and that's really where our focus is. The funding and all the effort that supports the ASCII program also supports all of the development of MCNP that I'll be talking about for the rest of the time this afternoon. MCNP is the principal Monte Carlo code that we have at Los Alamos. It's the base for all of our Monte Carlo technology that's used in other programs. This is where the basic Monte Carlo development is done, proof of principle and all that. It goes into this code. And we use this code extensively at the lab. We also distribute it around the world. MCNP5 is a particular version of the code that I'll be talking about this afternoon. MCNP first came out as an official computer code that was distributed outside the lab about 25 years ago, 1977. And that code has been developed and supported by the Monte Carlo team at Los Alamos for the past 25 years. At the same time that we've been supporting the code, we've also had a bunch of people that develop the data that is used by the code, the cross-section data for neutrons, photons, and electrons. So for the past 25 years, these two teams of people, the Monte Carlo developers and the data people, have been working together because the code is only as good as the data you put in it. And likewise, even if you have good data, it's not much good unless you have a good code to put it in. So the two work hand in hand, and we have been for 25 years. Today, both the Monte Carlo development team and the data team are in a group called X5. It's the Diagnostics Applications Group, part of X Division at Los Alamos, and we are part of what is called the EOLIS ASCII project. Now, the name EOLIS happens to be the name of some 14,000-foot mountain in Colorado. All of the ASCII projects at Los Alamos were named after the big mountains in Colorado. Not for any particular reason, but that's where the name came from. So we have in our Monte Carlo development team 12 code developers who work full-time on Monte Carlo development. The physical data team, also in our group X5, has about 6 or 7 other people who work on the cross-section data. And then also in X5, there are 2 application teams, people that apply MCNP and other codes to problems that are of interest to the lab. This is the current list of people that work on Monte Carlo development at Los Alamos in X5. And as I said, we have 12 people that full-time work on developing Monte Carlo methods. That's 12 PhDs that spend all their time developing things for MCNP. We get computer support for a lot of specialized areas, parallel processing, graphics, workstation clusters, and things like that from another bunch of people that work with us part-time as needed. We have a couple of full-time research associates. Taro Ueki, a postdoc that works with us, he and I are the ones that have been doing lots of research in the area of criticality calculations, the theory for Monte Carlo eigenvalue calculations. I'll talk about some of the results of that work later. The data team that develops the data that we use in MCNP. So we're all part of the same group. And then we have an assortment of people that consult with us or help out occasionally. So it's a large group of people working on Monte Carlo. Over the past 2 years, we did something that has been a lot of fun. Okay, we took this code that's been around for 25 years and we redid it. We rewrote every line of the code. Okay, so for those of you that have done code development, you realize that that's a big undertaking to take a code that works, that people have been using for 25 years, rip it apart, change it, and then put it all back together. That's what we did. Some more details of that in a minute, but first let me just say a few words about why we did this. This ASCII program, one of the largest programs that the DOE has, about $700 or $800 million between Livermore, Los Alamos, and Sandia. They buy us big computers, and we have to rewrite our codes to run on those big computers. The computers change every couple of months, or certainly every year or so. So our codes have to be very adaptable and flexible these days to run on computers that we don't even know what the next computer's architecture might be. So we have to be ready to run on essentially any sort of parallel computer, no matter how it's put together. Along with this, since this is a big-time DOE program, lots of money, lots of serious things on the line, so they demand that we adopt modern software engineering practices, modern software quality assurance practices. So we have to do a lot more stuff these days to prove to people that our software is being developed and works the way it's supposed to. So there's a lot of emphasis on that because of the ASCII program. So SQA and software engineering standards for Fortran and parallel processing. When we change computers every few months or every year, and when the computers themselves change, as they get bigger, as they reconfigure them and all that, we can't ever use stuff in our codes that is specific to some particular computer. Because as soon as they change the computer, that might not work. So we have to stick to standards. For the language that we use Fortran 90 and C, and the parallel processing that we do has to be in a standard form. We use what's called MPI for message passing and OpenMP for threaded calculations. So we need to adhere to standards so that we're pretty sure we can run on any machine that comes along. Another thing that we insisted on from the beginning of this effort was everything that's in the code has to stay there. Every capability it has, we need to preserve that. So just because we have a bigger computer doesn't mean we're going to throw stuff out of the code, even though that would simplify a lot of things. We want to keep all of the physics analysis capabilities that we have. And the most important reason for doing all this, I guess I've already mentioned a few times, we want to make the code very flexible, easy to modify, and easy to understand. We have lots of things that we want to add to this code. You'll hear about a few of them later. But instead of trying to take new things and patch them into an old code, we decided after 25 years it made sense to upgrade the code first, and then it'd be easy to put more and more stuff into it quicker. So all these things are driven by the ASCII program, what we're required to do to meet the DOE's rules, the ASCII program, as well as things we want to do to make the code more usable, flexible, and easier to modify. So MCNP5 started as MCNP4C3, the previous version of the code. And we didn't throw anything out, but we did rewrite the entire code. So we started with MCNP4C3, the last of the old style MCNP versions. And over the last year and a half or so, we redid every single line of code. Every one of them. Made sure it started out as about 45,000 lines. By the time we were done, it was about double that, close to 90,000 lines. So we made sure that everything in the code was completely conformant to the ANSI standard Fortran 90. We decided to stick with Fortran. The code was originally in Fortran, old Fortran. And we considered things like rewrite it in C or C++. And we have done things like that at Los Alamos. I was in charge of a large C++ code project for a few years, and we decided there was no particular advantage to entirely switching to a different language. By sticking with Fortran, we had a good basis to start with, and going from old Fortran to new Fortran made a lot more sense than old Fortran to C++. So we stuck with Fortran, but Fortran 90. We completely redid the build system, the install system for the code. So today we use the GNU utilities, GMake, and a bunch of other Unix utilities. So it's more modern method of compiling and changing and upgrading the code. Previous things were sort of homegrown back in the 60s and 70s, and we got rid of all those things entirely so that we use a modern build system. The most important thing to us, besides the fact that we want the code to still get the right answers, okay, but besides that, the most important thing was readability of the code, ease of future development, to sort of pave the way for the future, to put something in place that we could build on, and it made sense to redo the code entirely to make that happen. And how did we do this with 45,000 lines of code? Well, we developed some fancy Perl scripts. Perl is standard Unix scripting language, very powerful for matching patterns and making changes and manipulating text. So we developed some very fancy Perl scripts that did most of what we wanted. Some of the straightforward conversions from old Fortran to new, that was all automated by these Perl scripts. They were smart enough that if there was something they couldn't understand, they'd tell us about it and we'd go fix it by hand. Over this 18-month period, despite processing everything in an automated way with Perl scripts, we actually reworked about half of the code by hand and realized that we had about 12 people available to do this. That's still a lot of code to rework. Generally, every time we would make changes to the code, we would run a set of regression tests, 42 test cases, and make sure that those cases gave exactly the same answer as before we modified things. So these regression tests were run typically dozens of times per day. And that was one of the key things that let us do all this changing and still have the code work correctly. So we tested often, daily, many times. And these next couple of figures have to do with some statistics that we collected during this development process. Along the horizontal axis, it starts in 2001, ends in 2003, and this shows things like the total lines of code, how it grew from the 45 or 50,000 range up to about 85,000, 95,000 lines of code. So we kept track of some of this stuff as we were going along. Other things, blank lines. There were 0 blank lines in the previous version of MCNP. Blank line took up space or something like that, and they didn't want to do it, even though just simple things like blank lines can make your code more readable. So we put in about 8,000 blank lines. So out of the 90,000, 8,000 of them are blank. Okay, but it helps. I mean, it sounds silly, but it helps a lot. Some of the hardest things were things that were not so common, what are called computed go-to statements. Those of you that know Fortran, there's go-to, and then a list of statement numbers that are possible to go to. Well, there were about 200 of those, 150, 200 of those in MCNP, with not just 2 or 3 places to go, but typically 96 different places to go to. And those things had to be done.
We'll go back at that.
Yeah, those things had to be done by hand. They were very difficult to do. You couldn't automate that. So actually the most work out of changing all this code was in getting rid of those 150-some go-tos, computed go-tos, and getting that number down to 0, replacing that with more modern Fortran things. So even though we kept statistics, the most interesting ones are, they seem kind of little on these graphs, but they were the toughest one. Besides rewriting the entire code and still getting correct answers, we also added about a dozen new features to MCNP. And I've listed them here. I'm just going to highlight a few of them in the next few slides here. One of them is Doppler energy broadening for photon collisions. Typically, we think of Doppler effects when you talk about neutron physics and neutron collisions, but there are Doppler effects that apply to photons as well. That was previously ignored in MCNP, just not treated at all. So we added some more physics to the code to handle Doppler broadening for the photon collisions. In the blue here is the new MCNP, and in the red is the old MCNP. And this is for a source of photons at 88 kilovolts, which is right over here. This is the source energy here. The blue curve is right underneath the red one for that energy. But you can see in looking at this how the effect of the Doppler broadening tends to smooth out some of the sharp changes in things. So this could certainly make a difference in certain types of problems that you might want to analyze. So some new physics in this area, the Doppler broadening for photons. This is difficult to see the details of the picture, but this is a feature that we've had in MCNP inside of Los Alamos for a while. Neutral particle image tallies. We use this for generating simulated radiographs. When people do experiments these days and want to see what's going on inside the experiment, they will typically shoot things at it. It used to be X-ray.
It's called magic.
That's the other way I can change the slides, is cough. So it used to be that you shoot X-rays at something, or neutrons. These days we're talking about shooting high-energy protons at things, and they go through something, and then you want to see what happens. You want to generate an image, just like the image from a chest X-ray or something. Now, in order to do that, like for this example I've shown here, this is a 1 million pixel image, so it's 1,000 by 1,000 pixels. And essentially we have 1 million point detectors in the problem. Now, those of you that are a little familiar with Monte Carlo and MCNP, you know that point detector tallies are very expensive. Okay? Every collision, you have to take care of making an estimate at each point detector. So in the calculation that generated this picture, essentially every collision that happened, you would make a tally 1 million times at each of these point detectors, tracing the transmission from the collision points to each pixel in that image. And this is an extremely expensive calculation. This is one of the reasons we need parallel processing. The general limit in MCNP for point detectors is 20. We figured they're expensive enough that would ever want to use more than 20. It'd be such a slow calculation. Well, here's a case where we need 1 million. So we have some optimized coding. It essentially turns a few of the loops in code inside out to get better efficiency for making repeated point detector tallies. So an image like this, 1 million pixels, well, that's 1 million point detectors arranged in a grid to generate a simulated radiograph. So we can do this today with neutrons and photons. We are also in the process of putting things in the code to do protons as well. And there's various ways to plot this. Let me show you another case. On the left, we have a geometry model for an MCNP problem of human torso, a phantom. And we have shot things at that. In this case, I believe it was neutrons, but it doesn't really matter. And on the right is the radiograph that was generated by MCNP. And again, 1 million pixels, which is the equivalent of like 1 million point detectors in MCNP. So this is partly a good capability to have for analyzing some of the experiments we do, and as you can see from this, for medical applications, people are very interested in this kind of tally. We've added other things to the code, mesh tallies. In the past, we've had a mesh that would be superimposed on the geometry to provide weight windows. Well, we've done the same thing with tallies, so that you can define an arbitrary mesh independent of the geometry. It can cover a piece of the geometry or all of it, and you can define as many of these meshes as you want, and you can get tallies on the meshes. So this is another way to generate radiographs. It's also a way to get flux fields, like in a reactor, in a very convenient way. So we've added that. The criticality safety community has been after us for years to add some more edits to the code, things like the average energy of neutrons causing fission, or the energy corresponding to the average lethargy of neutrons causing fission. Well, we put those things in there. Okay, so those things that people are used to seeing in, say, Kino output, we've added a number of those to MCNP as well. New random number generator. On this slide, that looks like 1014. That's supposed to be 10 to the 14th. And down here, 10 to the 19th instead of 1019. I must have been dozing off at a long PowerPoint session. The traditional random number generator in MCNP has a period of 10 to the 14th. We allocate 152,917 random numbers per history, do the division, and you say, wow, after 500 million histories, we're going to start reusing those random numbers. That's correct. And is that a problem? Well, it used to be when computers were slow. Now today, it's pretty routine that we run 1 billion histories on lots of important problems. So that means we're using the random numbers twice around. We extended the random number algorithm in MCNP to use 63-bit, so the period is like 10 to the 19th, about 10,000 times longer than previous random number generator. And we put this in place in the code. We did extensive statistical tests to decide on the right parameters for random number generator. Statistical tests are two varieties as well as a spectral test, and this is now a standard feature of the code. Now, the default is we do it the old way, so people rerunning old problems get the same old random number generator, but it's easy to turn on the new one and get a longer period. Parallelism. For us, this is a huge thing. Our problems run long these days. People don't just run 1 million particles, sometimes they run 1 billion. And they generate radiographs a lot these days. So that takes a lot of computing power. So we run in parallel 2 levels of parallelism. At the higher level, we use MPI to distribute work to different processors, and then at a lower level, we can run threaded calculations with CPUs sharing the same memory. So we have these multiple levels of parallelism. Primarily, this is geared up to use MPI for the message passing and OpenMP for threading. Now, we also still support PVM, primarily because we have a bunch of users around the world that use PVM on workstation clusters. MPI won't really work very well on a heterogeneous cluster of workstations. It's more geared up to the big parallel machines that we have, or homogeneous clusters of workstations or PCs. But in any case, we like MPI best and recommend it. PVM is still supported. OpenMP for threading, and we can mix the two of them together. And we can do this sort of parallelism on any computer system we run on, whether it's PCs, Unix, or Linux clusters. And in fact, we routinely run 1,000 processor jobs with MCNP. Our larger users, or the users with the larger jobs at Los Alamos, typically run with about 1,000 processors. That's routine these days. Hero calculations with 3 or 4 or 5 or 6,000 processors, we occasionally do those, just to prove that we can, but sort of production mode for big calculations, about 1,000 processors. the graphics aren't as clear as we'd like, but this is one of the reasons we use parallel processing. Here is something done with actually a very slow PC. Resolution on this image is 21 by 21 pixels. And you can see it's not a very good picture. Now here, going to a resolution that's 64 by 64, so it's like roughly 10 times bigger. You can see there's better resolution in this image, and then if we go to even finer resolution, 256 by 256, we get nicer resolution. Now, the resolution, the number of pixels, and the running time is directly proportional to the number of pixels that you have, the number of point detectors. So these calculations, it's factors of 10 or 100 to go from the first to the second to the third there. And we can do this quickly, like in half hour, hour or something, when we run on these parallel computers using more processing. So the part of the point of parallel processing is more detail in the calculations, but do it without using much more wall clock time. Now, lots of CPU time with all the parallel processing, but wall clock time is what matters. And we routinely test and run MCNP5 on the biggest ASCII systems that there are. The Blue Mountain system at Los Alamos, the ASCII White system at Livermore, the new system at Los Alamos, the Q system. And we test with a couple of processors or thousands of processors on these systems, also a Linux cluster and a Windows PC cluster. These are the various computer systems that we support these days and run on routinely. Every time we put out a new version of the code, we have to test it on all these systems before we can release it. So we run on standard workstation systems, Unix systems, SGI, IBM, HP Compaq, Sun, Linux. We test with 3 different compilers on Linux, 3 different compilers on Windows PCs, and on all these systems, from PCs up to the largest ASCII system, we support graphics through the X11 X Windows system. Something that hopefully within a couple of weeks we will be running on Macs with OS X and the Absol Fortran compiler. This turns out nobody on the team had a Mac, so we never got around to it. So this was a good excuse last week to order the fancy, latest, greatest 17-inch screen Mac. So I made the sacrifice, and I'll probably start playing with that next week. Okay. And on all these systems, we demand that there be a Fortran 90 compiler, not F77 or G77. One of the complaints we get all the time is, the code works great, but boy, is it a pain to set up the input. And most of us agree, or some of us do. We have a couple of consultants, Randy Schwartz and Lee Carter, who developed something called the MCNP Visual Editor. And it's a GUI-based system. You see a snapshot of it there, where you can interactively set up the geometry. You can see it while it's being set up. And it uses the same coding for ray tracing and displaying graphics. It uses the same coding as is in MCNP5. And because of that, the visual editor and MCNP5 are pretty tightly coupled together. And in fact, when we distribute MCNP5 through RSIC, along with it will come this visual editor. Okay, just tossed in for people to use. Okay, so we're very happy with how that's coming along. Besides a new version of MCNP5, our data team is about to release a new version of the data. And this data is updated completely, so it's based on NFB 6, release 6. And there are 58 new nuclides in this release, so there's a total of 173 nuclides. The previous MCNP data set only had 122 different nuclides in it. So more nuclides, 40 nuclides have been completely reevaluated, and there's also coding that will be sent along with it so that you can Doppler broaden the cross sections without going through the full-blown NJOY calculation, to just take the data that we have in a very short code to Doppler broaden it. For those of you that do reactor calculations, this is pretty important. So that's part of the new package. Smaller tolerances in the NJOY processing, so the data will be more accurate. Finer points and more accurate interpolation. Things like probability tables, charged particle production, delayed neutrons, they are all built into this data set, whereas in the past, those things were in separate special libraries. Now it's all consolidated. We have spent a lot of time making sure the code is right. When we are doing our development, we run our regression tests many times a day. We also have run our criticality validation suite, which is 26 separate cases from the International Handbook of Evaluated Criticality Benchmarks. And we've run that both with the old data and the new data. We've run analytic benchmark problems for criticality calculations where we know the exact answer. And we have a set of radiation shielding validation problems, 19 of them that we run. And in all these cases, or almost all, when we run MCNP5 and compare with the previous version, MCNP4C 2 or 3, we get exactly the same answer. Not close, or not within statistics, but exactly the same answer. Now, there were a couple of exceptions to that for the criticality calculations. They're very sensitive to round off. Oops.
That's because the arrow's on the left. Get it off there.
All right. Let's do it there.
There you go.
For the criticality calculations, they're very sensitive to round off. If one history is just slightly different in one cycle, because you're iterating, any differences tend to propagate throughout the rest of the problem. So they're very sensitive to even a slight bit of round off. And we found in one case out of 2 that we ran, everything was the same for 600,000 histories, and then it differed by a little bit because of round off, and then it was off a little bit, but still matched within statistics the old code. So these sorts of verification calculations make us as sure as we can be that the code is still doing things correctly even after all we've done to it. This is just a list of the various criticality problems we ran. The only reason for having it here is just to point out we've run things with fast, intermediate, and thermal spectra. We've run things with highly enriched uranium, lower enriched uranium, plutonium, and all sorts of combinations of things, and all of these cases matched answers between the old and the new code. So we've run a variety of things. So where are we at this time right now? MCNP5 actually has been in use for about a year in our classes and testing within Los Alamos. Available on PCs, Unix, Linux clusters, plus the ASCII systems. We have had a few users outside of Los Alamos doing some testing on this for a while. In December, late December actually, I sent the code to ARSIC at Oak Ridge so that they could begin their testing. We've gotten some feedback from them. What's the holdup here? The code was essentially done in September of last year. So what is the holdup in releasing it? What's the manual? The manual is 1,000 pages long, and we decided we needed to update that to make it current and fix up a lot of things that should have been fixed up years ago. add some things about the response. So the manual, the holdup, is in the manual. Okay. So we expect that to be done within a few weeks here, and then the code will be ready to distribute. Okay. So we think certainly in March, R6 should be able to start shipping the code out to people on request. We have some things planned to put into it. More work to spruce up the code. I consider what we've already done to be sort of first round, and more stuff we'd like to do. There's other things in the area of variance reduction, pulse height tallies, and variance reduction that needs to be finished. It's partly finished. There's some other stuff that is being worked on pretty intensely now, proton transport. 50 GeV protons, and we're trying to get those into the code. That work's going on right now. We have about 4 or 5 people working on that full time, and that's to let us analyze some of the experiments that are done by Los Alamos. We have some things in the area of criticality analysis that we're actually quite excited about. This is some really new stuff, very interesting. I'll spend a couple of minutes just hitting highlights of that. The details are in a bunch of papers that we published, and we'll get to that in a minute. So we have a few other things we'll add to the code and perhaps release a version later on this year to include these updates. Everything I've talked about here at MCNP has to do with what we've done to the code and what we've added to it. But we spend a lot of our time doing research and development work in the Monte Carlo area, trying to figure out what do we need to add to this Monte Carlo code so that we can do better types of calculations, get better answers, or perhaps use Monte Carlo for things that people couldn't use it for before. The code runs on essentially every computer there is, and it's used for lots of different applications in the medical physics area, reactor analysis, crit safety, shielding, you know, a whole range of different applications. So we are continuously doing research and development to try and extend either the accuracy or the range of applications. And right now, for instance, the things I listed below there are research efforts that are ongoing right now, several of them in the criticality area. And I'm going to spend just a few minutes hitting the highlights in those. But we're looking at correlation effects, stationarity tests, calculating the dominance ratio, important quantity for reactors, and nobody can calculate it with Monte Carlo. Okay. Perturbation theory and some improvements in that. We've been looking at some medical physics things with special voxel geometries that match medical applications. Some more stuff going on with random number generation, random sampling. We do lots of benchmark calculations to help validate cross-sections. High energy physics. We have several people, as I said, working on 50 GeV protons and scattering reactions and so on for those. And then more work on variance reduction. I'm going to talk just quickly here, and I have references to leave about correlation and criticality calculations. When you do K-effective calculations with Monte Carlo, it's an iterative process. You take a bunch of points, you start a neutron at each point, you follow it through its history, and as it's going through its history, you collect potential fission sites that were caused by that original neutron. You do the same thing for another one and collect potential fission sites. So if you start here with the black points in one cycle, you follow those till they're gone, and then to start the next cycle, you use the fission points that were collected during that set of histories. So then you have a set of points for the next cycle. And you repeat this process over and over again for criticality calculations. Now, one thing you notice when you look at this, though, is if you have a large reactor system that might be 10 feet across or something, 12, 15 feet high, neutrons don't go over that whole reactor. They tend to cause fission somewhere relatively close, a few inches or whatever, away from where they were born. So one cycle, fission point there, the next cycle is going to have a fission point close by. So there's correlation in the locations of the fission sites between one cycle and the next, and the next, and so on. Now, correlation causes some complications for Monte Carlo. If you have positive correlation between events, that tends to increase the variance, the standard deviation. Now, most Monte Carlo codes don't account for that, so they will compute a variance that may be plus or minus this much, when the true variance maybe should be plus or minus that much because of the correlation. So we've spent a lot of time looking at this because the variances that are computed by people's Monte Carlo codes, yours as well as MCNP, are generally non-conservative. The variances are too small if there are correlation effects in the problem. So this gives us two things to think about. One is, how do we compute those variances correctly? The second thing is, well, in developing theory to explain this and handle it, maybe we will come across some new things that we can do that we couldn't do before.
It changed already.
Okay, good.
Yeah.
Telling me to hurry up.
Yeah.
So over the last 2 years, we put out 6 papers in this area. And I believe these are, when you put them together, this is the biggest advance in understanding the theory of Monte Carlo eigenvalue calculations in perhaps the last 15 or 20 years. So I'm very excited about this. And these papers are very hard to read. Okay. But in them, there are a couple of important things that I just want to touch on here, and then we'll stop. If we take the theory, just write out what's happening in a Monte Carlo eigenvalue calculation, where n is the cycle number. So we take the source for one cycle, we toss it into the Monte Carlo process, we generate new points that become the source for the next cycle. Like that. If we represent a realization of that source as an expected value without the hat, so an expected value plus a fluctuating component that should be small, we get an equation like this, which represents the propagation of error, of noise, from one cycle to the next in the Monte Carlo calculation, where we have an operator operating on the noise. In the last generation, we have some noise introduced by following the histories, and the particular error propagation operator happens to look like this. The details of it don't matter too much for now. What does matter is that when we model the Monte Carlo criticality calculations this way, that this is a linear Markov process driven by uncorrelated noises. Now, that may be gibberish to most of us, but as soon as you say that, there's a whole world of theory for statistical analysis that applies to this problem. And what we've done is made this connection, and then, based on this, we've applied all of the things that relate to linear Markov processes to the analysis of criticality calculations. And we've so what we've done is we expand the source and the error terms in terms of eigenfunctions. We look at what does it mean to operate on the terms in that expansion by this error propagation operator. When we do that, we get something which has a factor in it, k sub j over k0, where k sub j is a higher eigenmode, higher eigenvalue. K1 over K0 is the dominance ratio for a reactor, an important physical quantity. And this fraction is less than 1. So essentially this error propagation damps out by a factor of essentially the dominance ratio. And what I'm showing here applies to the errors in the source term. Okay? If we consider the same thing with the eigenvalue K effective, you have to remember it's an integral over the whole reactor. And when we take that integral of the error propagation operator and one of these eigenfunctions, we get the same term here, which it would be like the dominance ratio, so the errors would tend to damp out, but we get this additional term here, which is Kj over K0 minus 1. So it will be like the dominance ratio minus 1. Now the dominance ratio in reactors can be a number like 0.9999 whatever. So because convergence is difficult when reactors have high dominance ratios, however, when we consider the effects of correlation, we see that this extra factor here can make the correlation effects go away for K effective. Now, in a way, this tells us what our common sense tells us. Local quantities, the fluctuations matter. K effective, because we're integrating over the whole reactor, the fluctuations tend to cancel out. So we've finally proven some of this stuff that our intuition has told us for years. That's one important thing in this analysis. And here's an example of just what I'm talking about. Right here is K effective, and you can see it's converged in very few cycles, just a couple of cycles, and it's essentially converged, whereas the source, this is in the right half problem with a couple of halves in it, the source in the right half, however, takes quite a while to converge and then takes even longer to settle down. So the theory that we've looked at explains this fully. First time I've seen it explained, so we're very excited about that. Now, what's even more exciting is when you take all of that analysis, all the theory that goes with linear Markov processes, and you add into it an observation function, as it's called in Markov analysis theory. To us, that's the equivalent of something that takes the histories and maps them into a tally bin. So that's a simple way of looking at it. That when we add a tally, a localized tally of something like a source, we have a variation on this Markov process that we can represent as an autoregressive moving average and analyze it that way. It turns out when we do that and take advantage of some of the theory that goes with this, we can calculate, based on the coefficients that we calculate in doing this sort of fit to the data, we can calculate some of the coefficients and use those to compute the dominance ratio. And this is something that I've been trying to compute for the last 15 years with Monte Carlo. And I've tried all sorts of things, could never do it, and now for the first time we can do it. And this gives you an indication of how well we can do it. The dotted lines, dashed lines in this plot are a diffusion theory approximation. This is for a two-dimensional reactor problem, different sizes, so it's larger and larger as we go over to the right. The red is calculating the dominance ratio using transport code, discrete ordnance code. We consider that to be very accurate. And you see the Monte Carlo points on there with error bars, and what's very nice is these points out here calculated with Monte Carlo, the error bars are very small. Okay, so that's good because we're very, very close to 1 at that point, so we don't want large error bars. Physically, the dominance ratio cannot be larger than 1. So we're now able to calculate this dominance ratio with Monte Carlo, and to do it with what seems like excellent accuracy. That was 2 dimensions. This is a 3-dimensional problem. Dashed lines of diffusion theory, that's not the correct answer. The red line is from discrete ordinates. We believe that's correct, and our Monte Carlo matches that. So this is something I'm very excited about. Dominance ratio is a very important parameter for reactors. Stability, noise analysis, Enon things, BWRs, and so on. It's a very important quantity to know, and I believe this is the first time we've been able to calculate this with Monte Carlo. Finally, just another illustration of something new that we're doing in this area. In Monte Carlo, you guess the source you iterate and iterate and iterate, the source converges. You throw away the initial part while you were converging and just start tallying from then on. So the question always comes up, did you throw away enough cycles? Do you have a stationary converged distribution? And that's a tough question to answer. People have looked at that for 20, 30 years and come up with various ad hoc schemes. What we've done is look at a quantity called the Shannon entropy of the source distribution. Essentially, it's the average, the expected value of the log of the source distribution. SB sub I, that's the source in tally bin I, the B is the number of bins, and this quantity is defined as a Shannon entropy, something borrowed from information theory. It's bounded between 0 and the log of B, where B is the number of bins. And it has some nice properties. If the source is uniform, this entropy is at a maximum. If the source is all centralized in one bin, then this entropy is 0. So we've looked at this, and this is the result of one sort of way of looking at it. This is plotting the Shannon entropy in each cycle, one cycle delay embedding plot. So essentially, horizontal is entropy at cycle n, vertical is at n plus 1. And it starts out here, comes down this way. After a couple thousand cycles of iterating, we are then down here, and the entropy just sort of wiggles around in this range, so we can tell we're converged. Okay. This is a better way to look at this. The Shannon entropy starts here, and as we iterate and you get closer to convergence, it drops. And then, this is a logarithmic scale on the left, then it essentially stays small. Now, what's important here is this is 3 orders of magnitude that it decreases. Now, that's something that's pretty easy to spot on a computer. If something changes by 10% in a Monte Carlo calculation with noise, that's not too helpful. But when something changes by 3 orders of magnitude, it's easy to distinguish that from noise in the calculation. So we think this is a very effective way to see if we have a stationary distribution. And in this case, we would say if you threw away the first 500 cycles of this calculation, then you'd be fine. If you threw away anything less, you'd be starting tallies before you were converged, and that gives you wrong answers. So we think this is just an excellent way to test stationarity, and this is one of the things that will find its way into MCNP later this year. We're beyond the theory and the proof of principle now, and the next step is put it in the code. Same with these other things I mentioned. So these are just some examples of some of the R&D that we're doing that, assuming it pans out like it seems to in this case, that we will put into MCNP. And this stuff will show up this year, sometime later this year. So these are the things that we do to keep this code going for the long term. Okay. And we view that as just as important as our day-to-day commitments for the short term. We need both to fully support this code. So with that, I'm going to stop.
Okay, all right. We have time for a question or two.
Forrest, in the restructuring of the code, the computer science stuff, has the modularity changed? Are the subroutines still the same?
We have combined lots of subroutines into Fortran 90 modules. Now, we've done that in a sort of small way. We've grouped together the geometry plotting routines in a module, the cross-section and tally plotting routines, we group those together in a module. There's a random number module, and a few other modules like that. Now, we haven't gone and done some of the obvious things yet, like a cross-section module. We want to, but we said one step at a time, let's save that for a little bit. So we've combined some of the subroutines to Fortran 90 modules where it made sense and where they were easy targets. We have more stuff in that area that we're planning on doing. Okay. The code is it's different than it used to be. Now, if you're familiar with the old code, actually this code would be easy to follow and pick up because it is more readable. It's modern Fortran, not 1960s, 70s style Fortran. So, knowing the old code, you'd like this better, I think. I sure do.
Bill, you had a question?
Do you, just when you do the Arbor 2-1 modeling, do you assume the process is stationary?
Yes. Yes. In fact, what you just asked about is the reason we spend a lot of time looking at stationarity tests, because some of the work I described here, people have sort of dabbled in that over the years, trying to use signal processing techniques and so on for coming to grips with these correlation effects. And I tried stuff like that, 10, 12 years ago, and I didn't get anywhere. And one of the things we discovered is probably for the stuff I tried in the past, and probably for a lot of other people as well, they weren't careful enough about making sure they had converged to a stationary distribution. That they started doing their testing or their analysis of the correlation effects too soon. Now, while you're converging, there are large correlation effects, but they die away as the error transients go away. So if you start too soon before you've really converged, you're contaminating all your analysis with the convergence effects. So if you're really careful to make sure you're converged, and then you do your analysis, time series type analysis to find the parameters for the autoregressive processes and so on, if you are careful that you're converged when you do that, then it all makes sense and is consistent and holds together, and there's some very nice results. And what I suspect in the past, people weren't that careful about making sure they were stationary, and they included some of the convergence stuff at the beginning, and that gives you unpredictable results. And so in hindsight, when I look back a dozen years of trying to do this, I ask myself, well, what did we do right this time that I did wrong 12 years ago? And it's paying attention to the fact that you're stationary before you begin all that statistical analysis. So that is really important.
Okay. I do see a couple of new faces in the audience, and they may not know that we do have refreshments downstairs on the second floor after each of our colloquium presentations. And before we adjourn for refreshments, let's express our appreciation to Dr. Brown for his... Okay, go downstairs. He'll be down there. And we finally got the printout of it. But if you want to put it all together.
Sure. I'll be around for a while. I'm not in any hurry. If you guys want to keep that, you can.
If you have copies of that, I'd get that.
You want this?
Yeah.
Well, Forrest, why don't you put it